This is the 6-2 notes for Calculus 1. So far, in Chapter 5, we talked mainly about the concept of area under a curve. So if you look at the diagram, basically if we have some function f of x, and we want to determine the area under that curve between two specific values of x, then we would, as shown in the picture here, we would use the definite integral of a to b of f of x dx. Now, this section, which is a very good preview for a big chunk of what you'll do in Calc 2, basically talks about a different scenario. What if, instead of finding the area under one curve, you were asked to find the area between two different curves? So let's say we were looking at this. So we have a function f of x, we have a function g of x. We're looking for this area, which is not to the x-axis, but rather between the two functions. This creates another scenario that's not too complicated, but it's very logical. So why don't we just follow what that looks like? So suppose we're looking at this exact same example, but let's remove g of x from the diagram. So let's just leave f of x, which is the red curve right here. Suppose we decide that we want to find the area just under that. So what would we do? We would find the area of a to b of f of x dx, just like we did in the top problem up here, right? Well, why don't we then remove f of x from the diagram up here? So remove f of x, and instead we're just going to play around with the green curve, g of x. Suppose we wanted to find the area below that. Okay, so the area below g of x would be this. So if you're really smart about this and you look at these two curves, if I wanted to find the area between the two curves, all I would have to do is take this area and subtract this area from it. So real quick, if I just drew it in here, if I just drew the curve a little bit, so the curve looks like this, right? So if I drew that in and I took the purple area out, then what would I be left with? I would be left with what's in here, which happens to be the area between the curve. So interestingly enough, we can also take this from a derivation, because by doing that, we might be thinking of it in terms of area, but what also happened when we did that, we actually did the following computation. We did I'll do it over here. We did a to b of f of x dx, subtracting a to b of g of x dx. Now you guys learned already that the properties of integrals allow us to go in and out of integration as long as the limits are the same. So this is equivalent to this equation right here, which is essentially the definition of finding the area between two curves. So if you look down here, if you are looking for the area between two curves, then you can just use this formula to assist you when doing so. But one thing worth noting, this formula is with respect to x. So this is talking about a scenario where you have a curve on top here and a curve on the bottom, and you want to find out the area between them, between the two curves this way, from some value of x to another value of x. That is a scenario that we're concentrating on. Why do I point that out? Because in a couple pages into this, we're going to be taking curves now from left to right that have values of y over here. So just in the beginning, just realize that this is strictly in terms of with respect to x. So if you turn us, we're sticking with respect to x. So I do have a shortcut for you though. Students will often memorize this function up here, and they will get a little confused because sometimes they define these functions by f and g, but it's not really the f and g in this formula. I know that sounds kind of weird, but it can get a little confusing. So instead of thinking of it in terms of a formula with f and g, instead think of it this way. So you're going to be taking the area from some value of x to another value of x, where you're going to take the upper function and you're going to subtract the lower function. By upper and lower, I mean, of course, the one higher on the graph minus the one lower on the graph. If you use this, I find that students have a much greater success level when they use this formula more than anything else in order to accomplish what they need to do, and that's to find the area between the curves. Okay, so again, this is with respect to x. At some point soon, we're going to be doing with respect to y. It makes the whole topic harder, for sure, but I just want to point out for now, we are doing it with respect to x, and we know that, by the way, because of this dx right here is telling us that we're doing this with respect to x. Okay, so why don't we set up and do some example problems to make sure all is good. Number 1, determine the area of the region bounded by the graphs y equals x squared plus 4, y equals x equals 0, and x equals 3. Remember that the whole purpose of this is to find the area between the curves. If you look at the two curves that are provided, we have y equals x squared plus 4, which is our parabola 4 units up the y-axis, and we have y equals x, which is the line right here. Our goal is to find the area between them. You'll note, it's very important to note that the area between them actually goes on forever. So I could go on forever this way, like, right? All the way over there. As this curve keeps on going up, 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 the area goes on forever, which means in this particular problem, the area has to be limited to a certain range. So that's what these two formulas or these two equations are about. It's not always going to have to be that way. A lot of times curves naturally create compacted area, which I'll show you in a second. But for this particular problem, we need the limits at 0 and 3 in order for it to just be this area in this region right here. That is what we're looking for our problems. All right, so the whole point of this is to use the area formula we have up here in order to find the area between the curves. So let's do that. So A is equal to, we're looking for values of x which squeeze this area together. So values of x are on obviously the x-axis. It looks like the lines that we have here, the vertical lines, will be the left and the right region for that area, so 0 to 3. We then find our upper function, which is x squared plus 4, and we subtract, right, subtract our lower function, which is just x. And of course, we must include the dx. One thing to note here, for when we get to a different setup of this, is that note that every single variable is in terms of x in this problem. You got your dx, you got all variables on the right side in the equation are in terms of x, and then your limits are values of x. This is very important because we are going to be switching our variables to y soon, and then everything's going to have to be in terms of y, and you're going to have to know the difference between that. It's one of the more difficult things you do in the class visually. Okay, the rest of this is simply just doing a little manipulation. So when you look at this over here, sometimes there will be some algebraic steps that will be needed. You might have to distribute a negative, collect like terms. For this, there isn't any of that. So that's good. It's a good problem to start with just to get a basic idea of what we do. Instead, what we do is we just move around everything so it looks more familiar to us as a polynomial. We bring down the limits. Now, I know in the previous section, 5.5, you guys were like all strung up on and basically understanding substitution. Well, substitution, you don't want to get carried away. Substitution is used when there's an inner function, and in this problem, there is no inner function. I know you saw parentheses. That doesn't mean anything. Basically, in terms of this is just a classic antiderivative problem that you would have done in section 5.3. There is no substitution, so you just do it. Let's do it. Antiderivative x cubed over 3, x squared over 2 plus 4x, all evaluated from 0 to 3, no change of limits or anything like that. We then just have to substitute 3 and 0 into these. So we're going to get 3 cubed over 3 minus 3 squared over 2 plus 4 times 3. And then that's going to be minus, if you plug 0 in real quick into all of these, it clearly is going to be minus 0. If you do the math, you're going to get 33 halves as your result, and therefore the area between the curves. Okay, a couple things I want to point out here that are very, very important for where confusion starts to set in. First thing, this answer is always going to be positive. Okay? Always positive. Why? This formula here, the purpose of the formula, by saying upper minus lower, you're guaranteeing that the area computation will result in a positive. Students get carried away with the concept of, oh, so for example, there are some points where we're going to do problems where this area here is going to end up under the x-axis. That doesn't mean anything. The whole concept of the formula itself is forcing the area to be positive by doing upper minus lower. So realize this is not the same interpretation as a typical net area problem, so you will always get a positive. That's the first thing. The second thing, the directions for this problem are very similar to the directions for the total area problems we did at the end of 5.3. How do you tell the difference between them? It's actually quite simple, because the problems in 5.3 had one equation that you had to deal with. These problems have multiple equations. There will always be at least two that will provide it. Obviously, we got 4 here, but that's because we needed these two in order to limit the area to this. That will not always be the case. Sometimes the two equations will literally encapsulate the area, and you won't need to look elsewhere. So just realize these are two major obstacles for students in the beginning with confusion between other topics. So realize that that should help you a little bit more with everything else. Looking here, it says, note that sometimes the limits of integration are not provided explicitly. Therefore, you will need to find them by setting the two equations equal to one another. Why? Because that determines where the equations intersect. Okay, so take a peek at our next problem. It says determine the region of area of the region bounded by y equals x squared and y equals 2x plus 3. So you'll see that we have a line here and we have a parabola here. If you look, this is an example of where the two graphs actually encapsulate the area. So the area is not going to go on forever, but note, it doesn't provide you anywhere over here like it did in this one. It doesn't provide you what the values are where the areas go from left to right. So what you basically need to do, which is different than the problems that you've done before, is you need to find out, so here's your value here where the area is to the left. You need to find the x value, in which is the left side of the area, and then if you go here, you have to find the value that is the right side of the area. So this is basically the idea. when you do these problems, this is when it gets a little bit more visually challenging, is when you look at the problems, you're going to have to determine the left x and the right x. But this sort of summary here tells you how to do that. Well, note, these lines are actually drawn from where the two graphs intersect. And how do you find where two graphs intersect each other? You set them equal to each other. So we're going to do that. So we're going to write limits here because we want to find the limits of integration. And by doing so, we have to set our two equations, x squared and 2x plus 3, equal to one another. And by the way, why are we allowed to do that, to be clear? Because these are both equal to y. So all I would have to do is sub x squared. Since y is x squared, it's almost like a system of equations. I can put x squared right there if I want to. And that's exactly what I'm going to do. Okay, please don't let algebra blow up on you here. Students will look at this equation right here and they will lose their mind a little bit. Remember, this is whenever you're solving an equation, the goal is to get 0 on one side, especially if you have multiple variables going on in there. So you move it all to the left, and then it's factor city. You get x minus 3 and x plus 1 as your values. X is -1 and 3. So if you look at our graph, that means that our two limits are going to be at -1 and 3. This must be done. You cannot assume that this is perfectly in line with this 3 and that this point here is perfectly in line with the -1. You can't do that. You have to show the limit equations to get the important limits for doing the problem. Now we can go ahead and find the area between the curves. How do we do that? Well, area is equal to, we now have our limits. We have to take the area on the x-axis from -1 to 3. And now we have to take our equations and we need to subtract them. What do we start with? We start with the upper equation. The upper equation is the line. The line is on top of the area. So that is going to be 2x plus 3. Then we subtract the lower equation, which is x squared, and we do that in terms of x dx. Again, nothing drastic in terms of our algebraic steps here. This is just rearranging a little bit to make it more familiar to us. So -x squared plus 2x plus 3 is how we would write a typical polynomial, so it would be easier to do that in terms of the math. And then all it's about is just taking the antiderivative. So we're going to get -x cubed over 3 plus 2 times x squared over 2 plus 3x, all evaluated from -1 to 3. And a little bit of mini math here, we'll do x squared so that we can just go right into that in the next step. And then we have to evaluate. So this evaluation, of course, is not super fun. It's got both values, so it's going to take a while to get through, but we do it. So negative, it's going to be 3 cubed over 3 plus 3 squared. Remember, we're changing it to that. Plus 3 times 3. Okay, that is going to be minus. I'm just going to stagger the lines here. -1 cubed over 3 plus -1 squared plus 3 times -1. Okay, and that is equal to, you do all the math all the way through. I believe you're going to get 9 for this. You're going to get -5/3 for this. So when you put that together, you're going to get 32/3. And again, take note, a positive answer. So 32/3 would be the area between the curves. Note that these are two classic types of problems. You have the area of the bounded region, but then you have limits provided by vertical lines, or you have the area of the bounded region, region bounded, where you have encapsulated area by the two functions that provided. This is a very clear process that you have to go by. The biggest issue, of course, is simply seeing the diagram. And what I will tell you is you will always get the diagram in these problems, from me at least. So unlike all the other problems that you did where I'm like, you're not going to get the diagram, this one you will get the diagram. I do that just to make life a little bit easier for you while you're learning it. When you get to Calc 2, maybe they won't, but that's okay. They do go over this a little bit of a review, so they might expand on it a little bit. But again, note that the answer was positive for this one here. Same thing, upper minus lower is going to force a positive answer. Moving on. You will also run into scenarios where the bounded area doesn't always fall in the same region on the graph. In these situations, treat the bounded regions as separate calculations and make sure you pay special attention to which function is above the other function in each region. Okay, so we're looking at another area of the why do I have trouble saying that? Area of the region bounded by the graphs, where we have y equals x cubed minus x squared and y equals 2x. Looking over here, y equals 2x appears to be the line, and then we have a third degree polynomial curve going through the picture. Well, interestingly enough, when we actually do this intersection, it creates two encapsulated regions of area. One, of course, being here, right? And then one being in here, down here. What does that mean? Well, you've seen by the directions I gave you, similar to what we've seen before, we want to treat these as different regions, right? So I usually call them region 1 and let's say region 2. I try to stay away from the R1 and R2, by the way, because I don't want it to be confused with the previous lessons that we did in the end of 5.3. I just do Roman numerals here just to sort of help out with understanding with this. We treat them separately, but we still do the problem exactly the same way. And if you note, we don't have any x values where these are encapsulated. I think it's a pretty strong bet that this right here is going to be, that's a poor color for out here. This one right here is going to be likely at the origin at 0. But trying to figure out where these other are, we can make a guess where they are. So this looks like this is the rightmost, this is the leftmost. We can probably make a guess that it's -1, probably 2, right? But we can't do that. We actually have to, again, we have to set these equal to each other and find the limits. Just make sure that they're both solved for the same variable, because that's the only way you can actually set them equal to each other. In case I didn't mention that before, always solve for the same variable. Therefore, we can then set x cubed minus x squared equal to 2x. Why can we do that? Because since y is equal to 2x, I can put 2x right there, right? I just swap the sides. Again, we always want to make sure that everything is on the same side of the equation, equal to 0. You don't want to factor it like this. You need a GCF to be taken out of here. You're going to get x times x squared minus x minus 2. And then again, factor city here. We're going to get x plus 1, x minus 2. If we set all three equations equal to 0, all three, we're going to end up with x is equal to -1, 0, and 2. So if you look at your diagram, then that actually does verify that we have -1, 0, and 2 as the values where we actually will intersect the axes, or intersect the graphs with each other. Where on the axis does that happen? At what value of x? -1, 0, and 2. So again, this is all about finding the area of each region. So we split it up into two calculations. So the area of region 1, and by the way, I'll explain why it's split up into two calculations in a second. Area of region 1. What is region 1 separated into? It looks like it goes from -1 to 0. So that is those will be our limits of integration. What is the upper function in terms of it? Is it the curve or the line that's the upper function? It appears that the curve is above, so that's x cubed minus x squared, minus, and then 2x, which is our lower function, dx. So our goal now is to solve for this area. But before I do that, I want to do the original integral equation for the other region. If you look at the other region goes from, it looks like 0 to 2. But if you look super carefully at this region here, what is the upper function? The upper function is no longer the curve, but the line, which means that this time, for this region, it's 2x minus x cubed minus x squared. This is a huge deal, folks. This is a big stump for students. They often have a very difficult time following this in the beginning. This, because of the nature of the way this curve actually went together, the curve actually swung under the area till 0 and then over the area after that. Therefore, when you find the area of each region, you must swap them. Why? Because remember, the upper minus the lower is forcing positive area, which is the reason why you don't have to worry about that when the answer comes up. There's not going to be any absolute values in this scenario because you must force it to be that way. That is the best advice I can give you from the process. So again, why don't we do a little mini work here. So this is just going to be the way it looks, x cubed minus x squared minus 2x. But this one, not so easy. 2x, we have to distribute the negative to both of these. Therefore, when we organize, we're going to get negative x cubed plus x squared plus 2x. So basically, if you look at this equation and this equation, one is the negative of the other one. Just worth noting. All right, so once we have that as an equation, we can go ahead and integrate and do our simplification. So we're taking this equation here, x to the 4th over 4 minus x cubed over 3. We have minus 2 times x squared over 2. Clearly, this guy here is going to be just x squared, right? But we're evaluating that from negative 1 to 0. How do we do that? Well, luckily, if we plug 0 into all of this, right, 0 into all of these, we're going to get zeros across the board. So then all we have to do is worry about the negative 1. So we're going to get negative 1 to the 4th over 4 minus negative 1 cubed over 3 minus, remember this is just x squared, so we're going to get negative 1 x squared. Let me get rid of the other marker here so it stands out. If we do the math and put it all together as a whole here, we're going to end up with positive 5/12 as our area. So the area of region 1, which is this region in here, right, that is going to be 5/12. Down here, we have to do it again, the process. We can't, the other process when we did an n to 5/3 area of the region bounded, we could copy down. We can't do that because now we have a different equation. It is going to be similar. It's going to be the opposite of all the terms that are on the top. Let's skip right to this. So we're going to get plus x squared here instead of minus. And we're going from 0 to 2. So therefore, we're going to get negative, we have a 2 to the 4th over 4, 2 to the 4th over 4 plus 2 cubed over 3 plus 2 squared. Minus, and lucky enough, we have a 0 being thrown into all of these here, which creates 0 across the board. So what will we get? We will end up with 8/3 when you do the math of that. Therefore, the total area here of the entire problem is area 1 plus area 2, which is going to be 5/12 plus 8/3, which is going to give you 37/12 as your area of the of the region bounded. Still, man, jeez, I have trouble saying that. But my caution in any of these problems is just the similarity between this and one we've done before, but there are subtle differences that could cause errors. So make sure you look at this and say, okay, this is basically different than the other one because this is forcing positive area and we need to put it together, whereas with the other one, it is not, and it's only one curve. We'll need absolute values for that. So just a little bit of a side note for that. We're going to do one more, though, just to make sure all is good. Number 4, determine the area of the region bounded by the graphs f of x equals sine x, g of x equals cosine x equals pi over 2, and the y-axis. Integrate with respect to x. Okay. So when we're looking at this setup, note we've gone back to having 4 equations. When I say the y-axis, that is the equation x equals 0. Okay, y-axis, x equals 0. So we do have 2 values of x, and if you look at the graph, there's a reason why. If we take cosine and sine and go on forever with them, they are going to encapsulate area infinitely, which means there's got to be a way for us to stop the areas from side to side. So this problem, what did it do? It took the y-axis, which is over here, right? The y-axis, which is x equals 0. And then at x equals pi over 2, they stop the area on the right side, okay? This is important to see, obviously, because this has to happen or the area would go on forever. Alrighty. We must find the areas of each one of these regions because we need the area of the region bounded. We can immediately separate them into 2 pieces. Let's say region 1 and 2. We also are going to need to know where this point occurs because region 1, it looks like starts at 0 and then goes to here and then starts here and goes to pi over 2. Now, it looks like there's a ton of symmetry going on here, so it does look like pi over 4 is going to be that, but again, you cannot assume that. You must actually solve for these. So note that these are both y's. So since y is sine x, you can put sine in there. And what do you actually end up getting? Something very foreign looking probably to students. Sine x equals cosine x. Well, there are a ton of ways to solve this. What is this saying? It's saying, when is the sine equal to the cosine? At what value, what radian value? So most students will probably be like, oh, well, that makes sense. It's got to be where the y-coordinate is equal to the x-coordinate. At what radian value? And most students will go, oh, that's pi over 4, because that's root 2 over 2 comma root 2 over 2. That's one way to look at it. Another way to solve this problem is to divide both sides by cosine and get sine over cosine is equal to 1, which means sine over cosine is the same as tangent. So when is the tangent equal to 1? Well, we're only looking from 0 to pi over 2, and that occurs at pi over 4 because y over x is 1 only when the 2 coordinates are the same, and that's a pi over 4. So any way you chop it here, we are going to get pi over 4 as the limiting values. So basically when we're doing our limits, these are going to be the values we're going by. Let's do it. Since it's trig, it's valuable anyway, so let's check it out. Area region 1. Area region 1 goes from 0 to pi over 4. What is the uppermost function? Well, according to this, cosine is up here, and sine is down here. So therefore, we're doing cosine x minus sine x dx. All right, that's our first one there. What about the area region 2? We'll throw it way down here. Region 2 goes from pi over 4 to pi over 2. But, again, what happened here? What is the upper function now? Well, sine actually went above cosine in that region, which means we're doing sine x minus cosine x for that dx. Okay, we have our 2 equations, which is the point of this, is getting those equations and being able to work them out. So we can go ahead and do the integration. What is the antiderivative of cosine? It's just sine. What is the antiderivative of sine? It's negative cosine. Okay, remember, we don't have to worry about the whole 1 over a business because a is 1 in this problem, right? All the way through, and you'll see that a lot. We can then integrate this from 0 to pi over 4. We can, of course, change this to sine x plus cosine x. Why write it out again, though? We'll write a little mini thing below it so we can go right into doing the math. Okay, we can evaluate this. So we're going to do, it's going to be a little longer. So the sine of pi over 4 plus the cosine of pi over 4 for our first part. Okay. Then minus, we'll stagger it because we're running out of room, the sine of 0 plus the cosine of 0. Now, some of you are probably doing exactly what I warned you about. You're probably going, why don't you just put a big 0 here? Because you can't. By changing this to a trig function instead of a polynomial, we've changed the game when it comes to that. And I'll show you in a second what that's about. All right, doing the math out, the sine of pi over 4 and the cosine of pi over 4 are the same. They're both root 2 over 2. So we're going to get root 2 over 2 plus root 2 over 2. Then we're going to get minus the sine of, if you look at a graph, unit circle, where are we at 0 degrees? We're here. And what's the coordinate? It's 1, 0. So the sine is the y coordinate, which is 0, but the cosine is the x coordinate, which is 1. So you can see that this actually ended up being much different than we expected. Many would expect because of this is not all 0. Be careful with that. If you put this together, you're going to get root 2 minus 1. So this is going to be the area of region 1. What about 2? We are integrating but not the same equation. It's an alteration of it. What does that look like? Well, the antiderivative of sine is negative cosine. And the... hold on a second. Antiderivative of cosine is just sine. So we're evaluating that from pi over 4 to pi over 2. Okay, we can simplify this, obviously. Well, we can't really. We can just drop the, actually, let's just drop the parentheses. Right? Drop more than that. Oops. We got this. So negative cosine minus sine. We can then evaluate that without any issues. We could take out a negative to make life easier for us. I don't think it really matters too much, per se. So I'll just do it as is. So we're going to do negative cosine of pi over 2 minus the sine of pi over 2. And then that's going to be minus negative cosine of pi over 4 minus the sine of pi over 4. Okay, we already know what these guys are, right? This is root 2 over 2, and this is root 2 over 2. But what about pi over 2? So pi over 2 is up here, and that's 0, 1. So the cosine of 0, 1 is the x-coordinate, which is 0. And the sine is going to be the y-coordinate, which is 1. So if you put all of this together, we're actually going to get negative 1 plus root 2, which interestingly enough is exactly the same area as this, but just switched, right? It's just written a different way. So what does that mean? Well, look at the picture. Isn't it the same area? I mean, we're not going to guess that it's the same area in terms of, like, we're not going to assume it's the same area, but we can clearly look at these two pieces here and go, yeah, those are almost definitely going to be identical areas, and they are for the scope of what we're doing. So just realize that that's perfectly fine of result. So what do we need to do for total area? Well, the total area is the area of the regions added, right? I have no idea why I'm making the A bigger, maybe to make it more important. But we're going to do 2 times root 2 minus 1, or just adding these together. It doesn't matter. So we're going to get 2 root 2 minus 2. as the area of the complete region. All right, so before I move on to a change in orientation of the graph, so basically determining area between two curves with respect to y, I want to share something with students that often struggle with this material. So what I'm going to do is I'm going to return to the problems that we already did, and I'm going to talk about a concept that often helps students here, and if you're going on to Calc 2 even more. It's the concept of what's called a representative rectangle. So basically, if you're trying to find, we'll start here, if we're trying to find the area between two curves, and we know that we're doing it with respect to x, basically what we can do is we can take our region and make what's called a representative rectangle. Okay? So this representative rectangle essentially is our Riemann sum rectangle, but between two curves. And if you look at this rectangle, like any other rectangle, it's going to have a base and a height, right? So what would we do to represent the base of the rectangle? Well, the base of the rectangle was previously the change of x, right? So we replace that in our integrations with dx. So the base is dx. Well, what is the height of this triangle? Well, the height of the triangle is essentially the difference between the functions. So how do I know that? Because if I want to know the true height of this at some value, I would plug this value of x, let's just say it's 3. I would plug 3 into this function and 3 into this function, and then I would subtract those numbers to get the height. So all this is going to be is basically f of x minus g of x, whatever x is. So if you look right now at just this rectangle, the area is going to be this times this. Well, guess what? Isn't that this right here? So what does this mean? This means that we're basically taking this rectangle and extending it over a to b. That is where this is very helpful for students to see where this is all coming from. Essentially, this is a gigantic limit formula because we know definite integrals are limits, but we're expanding these rectangles over the whole area, but infinitely, in order to fill up that area. So just as an example, if we move to this guy here, our problem, let's say we made a representative rectangle within our picture. Okay? Because we're doing it with respect to x, we know that it's going to be a vertical rectangle. So respect to x means vertical. I call it a representative rectangle, but you can call it a rectangle if you want. Okay, so just real quick, what is the bottom of this going to be? It's going to be whatever change of x we have, which we represent as dx. What is this going to be? Well, let's say I wanted to know the height of this at 3. I would plug, well, we can actually do it at 2 just because we're closer over there, at 2. So what would I do? I would plug 2 in here and I would get 8. I would plug 2 in here and get 2. I would subtract them and get 6. Well, I want that, though, for every scenario. So what would I do? It would be x squared plus 4 minus x, the two functions. If I multiply these two quantities together, this and this, what do I get? I get this. And where do I want to spread it over? I want to spread it over 0 to 3. Okay, so hopefully that makes sense to you, that's what we're doing. We're just spreading rectangles infinitely over this. And I'll explain why that becomes more complicated in a second. But in Calc 2, you're going to be doing this in 3 dimensions. So you're going to be taking, let's say, like a rectangle and then rotating it around to create like a disc kind of thing or a washer. And when you do that, knowing these representative rectangles will be very helpful for you, because you'll be able to diagnose what you need to put in the equations when you're doing them. So why did I introduce that? Well, let's move on to the new topic. Now, if you look, sometimes equations are absolutely impossible to integrate with respect to x. Here's one here. Actually, here are three of them. If you look at this function, how on earth are you going to find a top and bottom function, first of all? Because there is no top and bottom function. And how are you going to find values from left to right when the area constantly is fluctuating from left to right? The answer is you really can't. I mean, you can, but it's an absolute nightmare. And by the way, just as a side note, there are functions that you can integrate with respect to both sides, and it's perfectly fine. We're going to do that at the end of this lesson. But there are some that you absolutely can't. So what do? So essentially, you create, again, a representative rectangle. So a representative rectangle with respect to y is a horizontal representative rectangle. Okay, so what does that mean? So that means this right here would no longer be the change of x, it would be the change of y, or in other words, dy. And what would this be? Well, this goes back to our formula for doing upper minus lower. We can no longer do upper minus lower, but we know on a graph that higher values are up and lower values are low. Well, what about on a graph on this way? Which values are higher and which are lower in the x direction? Well, values on the right side are higher than values on the left. So essentially, this would be f of y. Let me put a different color in here. This would be f of y minus g of y. So if we take these two and we multiply them, we need to then spread them over not values of x, but values of y. And you can clearly see we would spread them from c to d. So if you look at the formula, that's exactly what we're doing here. So we're taking the rightmost function minus the leftmost function, and then spreading them over values of y. And the best way to summarize that is with this. Okay, this little guy right here. So we're going to take values from smaller value to higher value of y, so up the axis, from the right function minus the left function, but again, important, make sure, I'm going to highlight it, make sure that you are using dy. So every single variable in this is going to be in terms of y. This is, the variables here are, and these are going to be in y. So if you find yourself in doing these problems mixing variables, so if you have a dx here and a bunch of y's here, it's wrong. If you have a bunch of x limits and then everything else is y, that's incorrect. So this is just a way for me to help you keep things organized. But that is a very important lead into this. So we're going to go through some problems here, 2 of them specifically, just to make sure that you understand the process of doing this. Remember, we still have to find those limits of integration. All right, number 5. It says determine the area of the region bounded by the graphs x equals negative y squared plus 10 and x equals y minus 2 squared. Integrate with respect to y. Okay. If you look at our equations, something has changed. They are basically solved for x. Now note, they're not always going to be solved for x, but in a problem where you integrate with respect to y, they must be solved for x. Just like in equation with respect to x, they must be solved for y in our equation. So you can see they're all solved for y. Okay, that must be the case so that you can do your substitution with the limits and so forth. So same thing goes for integrate with respect to y. They have to be solved for x. Make sure that you sort of keep that in your head. Now, if we're doing a problem like this, remember the goal is to keep it in respect to y. It is a challenge to make that change but the key right away is if you look at our type of area, it's encapsulated. So we don't need extra equations to let us know where it stops and goes, but we still need to be able to find those limits. So how do we do that? A little bit different this time. Since x is equal to negative y squared plus 10, that essentially allows us to put it in for x right here and get negative y squared plus 10 is equal to y minus 2 squared. All right, so we're allowed to do that. Now everything's now in terms of y because our limits are now going to be this way instead of this way. That's going to be the key. If we're doing in terms of y, then that's got to be the case. So we're going to get negative y squared plus 10 is equal to y squared minus 4y plus 4. Remember, you got a FOIL there. Do not forget that. If we need to move everything to one side of the equation, so I decided to move it to the right. So we're going to get 2y squared minus 4y, it looks like minus 6. Come out here, we can take a 2 out. Y squared minus 2y minus 3, then we go into factoring. We're going to get y minus 3, y plus 1. Setting all of this equal to 0 does nothing here, but it gives us y equals negative 1 and 3 as our values. So immediately we got to change our orientation. So where are the intersecting? Let me get a better value. So this, green maybe? Okay, there you go. Green, here and here. So now we're going this way. So it looks like negative 1 and 3 are going to be our key limits of integration. Okay, that's going to be how we're going to do this. Now, if you look at this real quick, this is only one region, so we don't have to do any region 1, region 2. We can go right into finding the area, and we're going from negative 1 to 3, so from here to here, right? Now, this is where the representative rectangle can help students. So right now, you might be looking at this graph right now and being like, oh my God, my head hurts. I'm changing the orientation of this. It's just very difficult. Rectangles actually help with that. So why? So let's say we drew a representative rectangle, right? So in a integration with respect to y problem, it must be horizontal. We immediately know that because the little side is over here, that's going to be, the little side is up and down, which means it's going to be the difference of y. This immediately tells us that we're going to have dy at the end of our equation. We also look at this and go, well, how do we find this, our actual length? Well, we have to take whatever the function is on the right, which is negative y squared plus 10, and we have to subtract whatever it is on the left, which is y minus 2 squared. So what are we doing basically? We're taking this equation times this equation to find the area of the rectangle, and then we're spreading it up and down from negative 1 to 3. So I'm hoping that all of you see that, because not only is that very valuable for sort of eliminating the stress of this concept, but if you are going to Calc 2, it's going to make an incredible difference for you when you start doing this in 3 dimensions. So what does this look like? We're going from negative 1 to 3, as we stated. We're going to have to do negative y squared plus 10 minus y minus 2 squared. dy. Okay, we have to write that. So be aware that you cannot forget that. That's the biggest problem that students have. They forget the dy. All right, a little bit more algebra than typical here. So this is going to end up being negative y squared plus 10. This is going to be, remember, when we square y minus 2 squared, we get this. So then we're distributing a negative and getting negative y squared plus 4y minus 4. So in the next step, what I'm going to do is I'm going to collect like terms. So we're still from negative 1 to 3, and we're going to end up with negative 2y squared. We're going to have a plus 4y and a plus 6. And we have to do that with dy. All right. Okay, so a little bit of you know, obviously we're not taking shortcuts, but we're just not writing it out. I'm making sure to show it though, so you can see with the math that was done, distributed property from here, with what's going on there, right there, right? Alrighty. So what's it all looking like here with going through the problems? We need to take our antiderivative. So it's going to be negative 2y cubed over 3 plus 4y squared over 2 plus 6y. All from negative 1 to 3. It looks like we do have only one simplification. This is going to end up being 2y squared, and that's it. Now it's all about just the math. So let's go down here since we need a lot of space. So it's going to be for our first quantity. This is going to be enormous. For our first quantity, we're going to do negative 2/3, 3 cubed, plus 2. Remember using this one. 2 times 3 squared, plus 6 times 3, minus. Same thing, but with negative 1. So negative 1 cubed, plus 2 times negative 1 squared, plus 6 times negative 1. And if you do all of that math, you're going to end up with, in the end, 64/3. What I'll do for you, since, there's a tendency for students to, like, I don't know, when they're going through problems, is to, like, ignore this, because they're like, oh, this is easy math, I'll know that, but trust me, don't. Do the practice, because, believe it or not, I get students who ace the calculus and then have just a trillion little minor math mistakes that just, it destroys their brains. They make them lose their mind, because like, how do I make that mistake? So try to do the math as you're going there. I put little green calculations in there so you know what the results were, but you are going to get 64/3 as the area between this region. Next problem. Determine the area of the region bounded by the graphs x minus y equals 1 and x plus y squared equals 3. Again, we're integrating with respect to y. Okay, right away here, we have a graph. It looks like we have a line, so this is going to be our linear x minus y is 1, and this is going to be our x plus y squared equals 3. Hopefully the first thing you note about what was given is that both of them have variables on the same side of the equation, which is not great for what we're going to do, so we're gonna tackle that in a second. So real quick, just to be clear on this, if we make a representative rectangle of this area, right? We know we're making a horizontal one because it's with respect to y, which makes this is dy, and then this is going to be this curve minus this line, right? Right away, what are we going to have to do with those rectangles? We're going to have to spread them where the area is located. Well, the area looks like it goes from here-ish to here-ish, right? So we can make a guess that it's going to be from negative 2 to 1, and I'm sure it will be for the problem, but that is what by drawing the rectangle, you can actually visualize what's happening. So instead of trying to just come up with the integration from scratch, you know what's going to happen, which means you can just look at the diagram and go, oh, okay, let's immediately just draw this in. Hopefully that helps. I don't know if it will, but hopefully it does. Limits. Okay, so and this is where it gets tricky. So remember, all of the integrated with respect to x problems all had equations where they were equal to y. Why is that? Because we need to set them equal to each other with x cubed minus x squared equal to 2x to find the limits. Then we got into our first respect to y problem, and everything was equal to x. Why? Because we have to set them equal to each other. Now, this is the first problem where they aren't, which means you have to look at what it's with respect to, y, know that you have to solve each equation for x. This is absolutely important that you do this. So this will be x equals y plus 1. This is going to be x equals 3 minus y squared. You must make this change. Why? Because now you can take y plus 1 and you can put it in for x, and you can actually solve for the limits. Y plus 1 is equal to 3 minus y squared. you would not be able to do that without this. So realize if it's respect to y, you solve for x. If it's respect to x, you solve for y. More work to just keep in your head. Now again, don't let this equation blow your mind up. It is, note that we have a single y exponent, we have a y squared and a number. That's a trinomial, we just have to get it there, which means we want 0 on one side. Since this is negative, I'm going to move the y squared positively over here, and I'm going to leave, the y stays, there's no like term, and I'm going to subtract 3 to get y minus 2. When we factor, we get y plus 2, y minus 1 equals 0, and therefore y is equal to negative 2 and 1, which is exactly what we expected it to be, okay? But you need to show this because you can't assume it. I'm being nice by giving you the graph, basically. So I'm going, this is, in Calc 1, I'm making sure that you understand the material. In Calc 2, if you are going to Calc 2, then you will do this again, like a review of this, and they'll probably not, maybe they won't give you the picture. And if they don't give you the picture, you would not see these values. I just so happen will. Okay, and by the way, in Calc 2, I don't give the pictures. Worth noting, because I've taught it before. So that I'm not surprised if they wouldn't. But I like showing you, I think it's important that you see them for the purposes of learning it here, and a lot of you aren't going to Calc 2, so I don't think it matters that much. All right, so let's take a look at the process. So we have now, we already set this up. We already know that we are expanding these rectangles from negative 2 to 1. We know that we have to take this minus this curve. So what's the rightmost? The rightmost is the curve, which is the y squared one. But you don't put this in the formula. That would be not so good. Instead, there's another reason why you solve for x, because now this goes in my equation as the rightmost function. I need to subtract now this, which is the equation of the leftmost function, y plus 1. And always remember dy. So you can see that giving you these equations up here, where they're on the same side, is a skill. That is something where you have to look at this, solve for it, and you won't get anywhere unless you do. So make sure that you are all good. So again, this down here is going to be through this, the length of this rectangle is that. So when you find the area of the rectangle, you multiply this times this and spread it up and down. Okay, that's sort of the key. All right, here what I'm going to do is I'm just going to collect like terms. So this is 3 minus y squared minus y minus 1. So if I put that together, I'm going to get negative y squared minus y, it looks like plus 2, all dy. Then all that's left is integration. So negative y cubed over 3 minus y squared over 2 plus 2y, all evaluated from negative 2 to 1. And then it's all about subbing all the values in, as we've always done. So 1 cubed over 3 minus 1 squared over 2 plus 2 times 1 minus negative 2 cubed over 3 minus negative 2 squared over 2 plus 2 negative 2. And then if we put that all together, we're going to end up with 9 halves when all's said and done. If you want to check your work, this is going to be negative 1/3 minus a half plus 2. This is going to be 8/3 minus 2 minus 4. Okay, so that'll help you out. Okay, so that is going to be a result of the area in this region. Okay, there's no doubt that this section is quite the undertaking. There's a reason why it's the last one. Hopefully the methods I gave you were helpful in sort of the learning mechanisms there with the rectangle and everything. I'm going to use the rectangle a lot now because it's going to get a little bit more challenging. I know that sounds intimidating, but it is. Why is this challenging? So if you look at this problem real quick, don't worry about the equation. Just look at the picture over here. So yeah, that's not, that is a highlighter. But anyway, if you look at the picture, you'll see that there is clearly a sort of a triangular region, but it's not a triangle because this is a curve over here. But it turns out that there are many regions where you can find the area with respect to x or y. And you will be tasked, ideally with finding the easier method for doing so. I know that sounds like a real challenge, and it is sometimes. But the purpose of number 7 and number 8 on the next page is to show you how you can find these areas separately. And I think it's very valuable because both of them, one of them almost always creates a more complicated solution. Like it's a more complicated integral equation to go through, where the other one's much easier. So that's going to be kind of the point of this. Now, you'll see for our problem, it's going to say integrate with respect to x for one and y for the other. Same graph. So when you look at this, that is going to be what this is about. And it can be challenging for the brain. It's one of the hardest things you do, but hopefully you can stay with me and get that. One small thing, though, before we move on. Everything in number 7 and 8, I'm not going to do the actual computations for. All I'm going to do is set up the integral equations so you can see them on how you're going to do them. I often, when there are in-class exams, I actually do that as well. I do a couple problems that are just give me the integral equation, don't compute it. I don't know how I'm going to do that this semester yet because I didn't make the exams, but just to note that is the case. So we're not going to actually find the area in these. I'm going to give it to you, but the goal is to see what the integral equation is going to look like in each one of the methods for respect to x and y. All right, reading the problem. It says, determine the proper integration that would allow you to find the area of the region bounded by the graphs of y equals 4x squared, y equals 3x, and the x-axis. Just to note, the x-axis is the equation y equals 0. Okay, it does say use technology to confirm the integrations. Don't worry about that. I'll make a note of that later. So our first task is integrate with respect to x, which means we must draw a vertical representative rectangle. So let me just, for example, draw it here. Okay, so if I draw this rectangle right here, the bottom of the rectangle is clearly going to be dx because it's left to right. But the difference with the rectangle, top to bottom, is going to be this line minus this line, okay, down here. So in a sense, we're looking at a triangular looking region. But my question is, if I was to spread this rectangle all the way from 0 to 2, which is what we would do normally, am I going to get the same upper and lower function all the way across? Okay, hopefully you look at this picture and say, absolutely not. The lower function is uniform all the way through, but the upper function actually changes throughout this diagram, which means this is a problem where I would need two representative rectangles, where the dx's would be the same, but the heights would be different. Why? Because we have a line split between these regions in which they are different. And by different, I mean there's a different calculation for that area between the upper and the lower function. Okay, so this is super tricky. So what are we looking at? Well, what I want to do real quick is I just want to label, so let me get a different color here. So this basically is going to be we'll just call it 2 and 1, region 1, right? So I'm not going to do region 1 and 2 over on the left, but I'm going to form the equation for the area, and I want them to be separated. So let's look at region 1. Region 1 is just going to be basically this actual rectangle right here, right? And this rectangle has an upper function of 3x. How do we know that? Because when we do integration with respect to x, all the equations must be solved for y, which they are, which means this equation is 3x. And what's the lower equation? Well, what is it actually going to? It's going to the x-axis, Well, what's the equation of the x-axis? It's y equals 0. So what am I doing? I'm doing 3x minus 0 dx. And I'm going from 0 to 1. Now you might look at this and go, well, wait a second, isn't this just 3x? It is. There's a reason for that, folks. Because don't we normally, when we do typical area under a curve problems, don't we go to the x-axis? And do we ever do area between curve formulas for that? We don't. There's a reason for that, because it's always minus 0 with the bottom curve, which is why this ends up just being 3x dx. So what we also need to add to that, region 2. Well, region 2 actually goes from 1 to 2. All right? And just in this scenario, for our 1 to 2, where do we get that from? Well, our graph actually has a grid on it, right? And the grid tells us it's at 1. That's where it's going to, how it's split up. How would we find that? Again, we would just set these two equations equal to each other and find the limits. But since we have a grid on this specific graph, it actually allows us to say it's definitely 1. All right, so from 1 to 2, now what's the upper function? The upper function is the curve 4 minus x squared. Again, what's the lower function? It is y equals 0. But looking through and seeing this, what is that going to just be? It's going to be 4 minus x squared, because if I asked you to find the area under this curve normally, you would just say 4 minus x squared dx. That's it, because it's going to the x-axis. You're used to going to the x-axis all the way back to section 5.3. So now it's just seeing that formula, there was a reason why they didn't include any subtraction. It just so happens that the bottom of the graph is 0. That's all. Okay, so basically, what is the answer to the problem in terms of just the integral equation? It's this. Okay, that is it. Okay, that's what I would be looking for most intensive purposes. Note that if technology tells us that this is equal to 19/6. So by technology, I mean there's various websites that allow you to find integrals. Even Desmos has a built-in ability to do so, but the area ends up being 19/6. So what if we needed to do this problem and with respect to y? What would change? Well, the first thing that you want to tackle, first of all, in the scope of this, is just that our equations in our first problem were clearly y equals 3x, and then the curve was y equals 4 minus x squared. This was okay because we were with respect to x. Now we're with respect to y, which means we need to solve those equations for x. That is our goal. That's what we're going to have to basically figure out for the purpose of this. So what does that look like? So if we change y equals 3x and solve for x, for this, we're going to end up with x equals y over 3. Okay, so now instead of this, we have this. We're also going to have to solve for x for the curve equation. If we do that, we're going to get x is equal to the square root of 4 minus y. But I want to make a note of something over on the side here in solving. So if we have this, right, let's just say we add x squared over here and we subtract y over here. If we take the square root in the next step, we're going to get x is equal to plus or minus root 4 minus y. So note, the plus or minus is actually quite legitimate on this one. So on this side of the curve here, this side of the curve, the equation is the positive square root of 4 minus y. But on the other side of the curve, the equation is the negative square root of 4 minus y. This is important. This will come up much more in detail in the next problem, but note that that is the case. Now that we have the equation on the graph, we can concentrate on our representative rectangle. So remember, representative rectangles for respect to y problems are drawn horizontally so that the up-down part of it is dy. That means that if we want to find the length, we're basically going to have to do the curve here minus the line here for the scope of our problem. My question is that the case all the way up and down? So, by the way, up and down would go from here to about here in terms of heights, which is 0, and since we have a grid, it's going to be 3. So we're spreading this rectangle instead of left and right, we're spreading it up and down. So by doing so, we're going from 0 to 3. Anywhere in there, does the right and left side function change? Hopefully you're looking at that and saying the opposite of A. It doesn't. It's the same all the way up and down. Now here, in this equation, it changed because as we went left to right, the top function actually switched places from the line to the curve. So we needed 2 regions to pull this off. For this one, we don't. So what does that area then look like? Well, the area, we just said, spreads from 0 to 3. We take the rightmost function, which is going to be the positive root 4 minus y, and we subtract the, actually I don't need the parentheses because I have the radical, and we subtract the left function, which is y over 3, and we must do it with respect to y, and this is it. This is your integral equation that you're going to have to work with. And note, there's a reason why I'm not having you solve these, because they are nasty. Some you might not even be able to do with what you know so far, some of these integral equations. So worth noting, you put this into technology and you will indeed get an area of 19.6. Look. If you're integrating with respect to x and y and you get a different answer, there's a big problem. Because either way you do it, it's still the same area, so you should get the same answer. So by doing each of these, that's exactly what would happen. So right away, which one of these is the easier one to do? Definitely B by a mile. Anytime you have to do more than one representative rectangle, then you have an issue. When you have to split up the regions, it's a headache. You didn't really necessarily see as much of the headache because you didn't have to do double the integral work over here. I just showed it to you, but it is just a gigantic headache. Ideally, we would do it with one equation with respect to y, but these are the integral equations for finding these pieces. Seeing the difference between one to the other and how they work is very important, hence, and also why I use this representative rectangle to help out with the process. Alrighty, so one last problem in the semester. Another problem with respect to x and y. Again, just the equations. This is, believe it or not, even nastier than the last one. Alright, so what are we looking at here? We're looking at area of the region bounded by 2 functions. X equals 1/2 y squared minus 3 and y equals x minus 1. The first thing you should note is that one is solved for x and one is solved for y, which is completely nasty, right? So we know right now, though, that we're going to have to solve each of one of these eventually for the other variables. So I say, let's just do it now. So this would be x equals y plus 1. This is going to be equal to y equals, again, plus or minus 2x plus 6. Okay. So if we're doing with respect to x, that means we're doing vertical representative rectangles again, right? And we're dealing with all the equations that are solved for y. So if you look at this right now, these equations that are listed on the picture are not solved for y. So we're going to basically just scrub them out for a second here, right? So this was in the original equation. I probably will eliminate that in my next version here. So what are we going to do? We're going to put these equations on the graph. So the curve is going to, or let's do the line first. The line is going to be y equals x minus 1. Okay, and the curve is going to be y equals plus or minus root 2x plus 6. But again, in a different orientation, anything above the axis is going to be y equals positive 2x plus 6. Anything below the axis is y equals negative square root of 2x plus 6. This is something you've probably never seen before, but it is important to what we're doing and when we go about this. Next, what about a representative rectangle? So let's say I drew a representative rectangle right here. Okay, clearly bottom dx. The top function appears to be root 2x plus 6, and the bottom function appears to be x minus 1. If we move this rectangle all the way left and right, does it always have the same top and bottom function? If you quickly peruse to the right, it does. But if you keep going to the left, when you cross over this right here, then we have a very big problem. We end up with a different representative rectangle again on this side, where the upper function is positive to root 2x plus 6, and the bottom function is negative 2x plus root 6. So, or root 2x plus 6. So just, it can get very nasty. This is a welcome to calculus 2 kind of a speech right here, but that's pretty much what it's going to be like. So in this perspective, this is another example where we're going to have to do a double region in order to set this up and make it work. Okay, in order to do that, we must separate the regions into pieces. So it appears, remember, we're on the x-axis here. So it appears that the regions are going to be split up at -1. There are no grid points, but I've already shown you this a million times. You have to set root 2x plus 6 equal to x minus 1. So root 2x plus 6 equal to x minus 1. Square both sides, blah, blah, blah. And then go from there, and eventually you'll end up with ... You're going to end up with -1 as your key value, because that is where they intersect. Now, you're also, by the way, going to get another value out here when you do so, but the one we need is -1, because that's where the area is split up. So what does this look like in terms of how we're going to do this? So the first region, we're taking this rectangle with this rectangle over here, with dx on the bottom, and we're going this minus this, right? And we're spreading the rectangle from -3 to -1. -3 to -1. And we're doing the topmost root, I don't need a parenthesis, root 2x plus 6 minus the, actually I will do it this time, the lower one, which is negative quantity root 2x plus 6 dx. So that is the first region. So what will that find? That'll find this area right here. I don't know if you can see that, so I'm going to do it here. Find that region right there. Now we must find the other region, which is over here, right? So how do we do that? Well, we have to add to this. So I'm going to I'm going to stagger, big add. This time we're spreading the rectangle from -1 all the way to 5. Now, again, if you solve this here, I feel like I should. I feel like I'm skimping on you here. So let me just solve this. Just the square minus 2x plus 1, right? And we're going to get 0 equals x squared minus 4x minus 5, which is going to give us x minus 5x plus 1. X equals -1 and 5. Okay, there you go. So, just so I'm not shortchanging the process. So we're going to get -1 and 5. And so we're going to go here. This time, the upper function is still root 2x plus 6. 2x plus 6. But the bottom function is no longer this. It's now this line right here, which is x minus 1 dx. So what you would basically do is you would do all of this integration, which again is not so fun. We're not going to spend the time doing that. If you go to technology, you're going to find that the area is 18. Okay, but this is the answer to the problem for what I would be looking for if it just says determine the proper integration, so, or the integral equations. That would be it. So that's a disaster area, right? This is definitely not going to be the preferred way to do this, but it just shows you how crazy this can get. Now let's go with respect to y. The equations themselves need to be solved for x, and it turns out that they are indeed on the picture. Note there are no pluses or minuses in this scope of things. It's just x equals 1/2 y squared minus 3 for the whole thing, x equals y plus 1 for the line. So what is this all about? Again, what are we doing? We have our equations. We draw our representative rectangle, right, which has up and down of dy, and all we have to do is we have to do rightmost function minus leftmost function in order to find the area. What are we spreading this over? Well, it looks, again, these are where we intersect, right? So if we're looking at this from this point of view, we'd be setting 1/2 y squared minus 3 equal to y plus 1. 1/2 y squared, bring the y over here, bring the 3 over, minus 4. We hate the half, so we're going to multiply everything by 2 and get y squared minus 2y minus 8. Alright, so if we factor, we're going to get y minus 4, y plus 2, and we're going to get y equals negative 2 and 4. So if you look at this, we are spreading from negative 2 to 4 this representative rectangle all the way up and down. Is there anywhere where the right and the left change? In this case, no. That can be confusing for students because they'll say, well, when it goes below, doesn't it change this equation? It does not when it's not a square root. It only changes the sign of the equation when it's a square root function. It does not when it's a square function, which should make a little sense because when the variable is squared, it's going to take care of the negative and make it positive anyway. So what does that look like? So we have the area is equal to, we're spreading from negative 2 up to 4 values of y. We're taking the most right function, which is y plus 1, and we're subtracting the most left function, which is 1/2 y squared minus 3, and we're doing that in terms of y. So see, this is much easier integral equation, and yes, if we verify this with tech, the area will be 18 as the result. And just to point out, notice real quick what I was talking about before. Biggest mistake that students make in this section is interchanging variables. So if this is with respect to x, everything, every variable in this entire equation and every limit in the entire equation is an x value. All of it. All an x value. Whereas if we go down here, this is respect to y. Every variable is a y variable. Even the limits are in terms of y, 4 and negative 2. It's very, very important that you get that. Now, on an exam situation, FYI, I don't usually give you insanity like this, I'll be honest. This is great for in class and in labs and practicing and homework. But when it comes to exams, I am very more clear, like you might get something like this. This is not a hard problem to do in terms of y. You could even integrate this, okay, because it's a polynomial. So just realize that the skill level of the exam is going to be a little lower than this, honestly. You're going to need to be able to do it for labs and such because that's where you're getting pushed in the class. So just realize that that is the case. And it looks like it's a wrap on the semester.